In ring theory, we have rings, subrings, and ideals. Ideals are like normal subgroups because they're going to help us, instead of forming factor groups, we're going to form factor rings. A subring A of a ring R is called a two-sided ideal. Evidently, there are one-sided ideals as well. If for every element R of the ring and every element A of the ideal, both of these products, RA and AR, are in A. Notice R doesn't have to be in capital A, yet the products are still in capital A. In the lectures, I call this super closed. RA and AR get sucked into A. Another slurping sound. Think about it visually. There's your ring R. There's your ideal A. Little a and is in capital A. Little r might be in capital A, but it might not be in capital A. Yet when you multiply them in either order, R times A or A times R, which are not necessarily the same because we're not necessarily talking about a commutative ring here. R times A and A times R are in A. Let's draw them as if they're different. R itself is not getting sucked into A, but by multiplication times elements of capital A, the product gets sucked into capital A. Superclosure. It's almost like it's collapsing the entire ring to A or something. That's not literally what's happening, but it's just kind of a fun thing to imagine. Okay, that's the definition of an ideal, a two-sided ideal. We will only talk about two-sided ideals, not one-sided ideal. Yeah, capital A absorbs elements from capital R. If you define these sets, R capital A or A capital R, which kind of look like cosets, don't they? Though they're not in ring theory. We're going to write ring cosets in ring theory with plus signs. But you can still define these sets. R times capital A is the set of all products little r times little a, as little a varies over capital A, and similar for capital AR. These are both subsets of A. A brief definition, though it's not labeled as a definition, is that an ideal is a proper ideal of R if A is a proper subset, meaning it doesn't equal all of R. All of R is an ideal of R, but not a proper ideal. You might wonder, why is this mentioned? It comes up later in the chapter. Just like there's a normal subgroup test, there's an ideal test. A non-empty subset A of a ring is called an ideal if, first of all, it's closed under subtraction, so it's a subgroup. Actually, we already, yeah, okay, that effectively verifies it's a subgroup under addition. That's like the one-step subgroup test, because the group operation's addition, so that we're using a minus sign for inverses. And this second condition both verifies closure in the subring. A is a subring. That's like the subring test if R is actually an A. But if you only assume R is in capital R and possibly not an A, it is also enough to verify that it's an ideal that's super closed. So yeah, we have had a subgroup test in the past. We had a normal subgroup test in the past. Recently, we now have a subring test, and now we have an ideal test. I always found it kind of exciting to use those tests when I was learning it. The subject was like, I'm going to use that normal subgroup test to